Hey everyone, welcome to my latest video where I'll talk about the newest meta model called Llama 4. It's the natively multimodal model that has been subject to a lot of critics recently, mainly because of their lack of accuracy. This video is going to be a bit different than other videos I had so far because it's going to be quick, short, and it's going to be focused mostly on the coding aspects of it. But I'll still spend a bit of time going through this research paper to show you key insights. So when it comes to the Llama 4 model, they created three different versions of this model called Behemoth, Maverick, and Scout. Behemoth is the biggest model, which has the most number of active and total parameters, while Scout is the smallest model with the smallest number of active and total parameters. Because the Scout model is relatively small, it's able to run on a single NVIDIA H100 GPU, or at least they claim it. When it comes to architecture, they're using the mixture of experts architecture. So this is why they have different number of active and total parameters. For those who are not familiar with the mixture of experts architecture, this is an architecture where you can only activate a set of parameters depending on what's the topic or context that's being discussed in here. For example, if we're talking about coding, we can only activate expert 0. If you're talking about sports, we can only activate expert 1. And then depending on the tokens that are coming in the router can route these tokens only to one or the other experts. And this way we can save a lot on the computation. When it comes to the computation, we can also mention that this model has been trained in float 8 precision, which has been pretty standard with the recent models. I mean, they're saying it's without sacrificing quality, which again, it's semi-true with the recent models, but it can definitely be achieved. And this is very different than float 16 or bfloat 16 that was used for many models only a year ago. They also mentioned, fun fact that they've been using 32K GPUs to train this. When it comes to the post-training, there's nothing really interesting here. They're doing pretty much standard stuff. They're using the lightweight supervised fine-tuning, which is something that we also seen with the DeepSeek. Then they're using the online reinforcement learning, and they follow by the DPO. So pretty standard stuff, I would say. So let's quickly jump through the code. So I have in my repository a script where I was able to run Llama 4 Scout model, at least the quantized version of it. I will not go deeply through this code, but I'll just quickly show key insights. And I would say the main insight is really that as I've been using the Hugging Face as most engineers are to load and run this model is pretty big. So not only you have to quantize it, you have to be careful that during loading, you offload some of the parameters to CPU, otherwise you would crash the GPU, even if that GPU is H100. In my case, it was actually the even stronger GPU, the latest NVIDIA GPU, Blackwell 200, with memory of 100 and I think 90 gigabytes, and it still crashed. So because of this, I had to use this device map where I set a max memory on 0, which essentially means Q to 0, like 0th core of GPU, and on CPU. After the parts of these parameters or weights is uploaded to the CPU, I load this model with from pre-trained method from Hugging Face API, and then we have multiple choices. We can either use distributed inference framework such as DeepSpeed, or we can move these weights to the GPU. So what I decided to do here is instead of using this distributed framework for inference, I am manually moving these parameters to the GPU. And once the parameters are moved to the GPU, you can just run the inference normally with Hugging Face API. So yeah, feel free to check out this script. I'll post the link to this script in the description of this video. And also feel free to check out other scripts I have in this repo. They're not only related to the inference, but they're also related to the fine-tuning, preference optimizations, etc. And I'll also be adding new scripts here over time. So and adding more descriptions so you'll be able to run it.
So let's jump straight to the code. So here you can see the repo, which contains the Llama 4 model. I'll share the link to this repo in the description of this video. So if we click here on the model.py, we can scroll to the bottom and we can go from the most high-level component and then work our way downstream. So essentially, the most high-level component for them is this class transformer, which is extended from PyTorch NN module class. So class defines in their constructor all of the variables that are going to be used for this transformer on the high level. So we can see they're using the token embeddings, which is the type vocab parallel embedding. This is just a typical embedding class, but with the exception that it's parallel, which essentially means that it can be processed on multiple GPUs at the same time. So this is for efficiency. Then you for each of the number of the layers, you're adding a new transformer block. We're going to dive into that later. Then we have RMS norm near the end, and at the end we have the parallel linear layer, which will output the logics. As we know, RMS norm is fairly widely used by Llama models, mainly because it's computationally much cheaper than, for example, layer norm, because you don't have to calculate means. So yeah, further they're calculating for rotary embeddings, sinuses and cosinuses. I'm gonna dive into this later. And then if there are vision arcs, which means the model is multimodal, then we also create a vision embeddings and we project this vision embeddings. And at the end, we register prehook and state the prehook, and then we provide load hook method to this argument. This is mainly only used for optimizations purposes, so I'm not going to be diving deeper into this. If we go into the forward method, which is, as we can see, executed in inference mode, we're pretty much doing everything I explained above. So we are getting the tokens, we are getting the starting positions, then we are getting the embeddings H after we pass these tokens through the token embeddings. Then if there is an image embedding, we get the image embedding as an H image. Then we use the image mask to interleave this image embedding with this original H embedding. So in the end, we get H embedding, which is pretty much contains both text and the image data. This is why Llama 4 is called to be a natively multimodal model. Then we calculate the cosinuses and sinuses frequencies that can be used for rotary embeddings. And then if the sequence length is bigger than 1, we also get the global and local attention mask, which will be used later for autoregressive um, predictions. So we don't have to look, so we can only look back in time. We never look forward in time. And then we go through all the layers pretty much, and we pass the data through all the layers, and then once that's done, we pass it through the RMS norm we talked about before, and then in the end we get all the logics in the float that can be used for the prediction. So now the next block is the transformer block, which makes each of the layers. So in this block, we can also define many different variables, such as number of heads, dimension. Then the head dimension is the division between the dimension and number of heads. We also define the NOP layer. The NOP layer is the layer that doesn't have the rotary embeddings. This essentially means, as you know, the rotary embeddings encode rich positional data, so NOP layer will have no positional data encoded in it. Which means that we'll take more look at the context rather than the positions where each token is appearing. Then user OP is obviously the opposite of the NOP layer. Then use the QK norm. QK norm is usually used for stability during the training, but can also be used during inference. And then finally, we define the attention. We have a couple of checks here. So if we are using the mixture of experts, as I talked about before, and then if we are at the light layer, then we can define the feed-forward layer to be the type mixture of experts. If that's not the case, then we have the fully dense linear layer. In the fully dense linear layer, they're using typical Llama dimensionalities. So for the first layer in the feed-forward layer, they're gonna be using 4 times the dimension of the attention, and then the next one will be 2 times the dimension of attention divided by 3. This is something that they discovered empirically to work really well. And then we define the attention norm, we define the feed-forward network norm, and finally we load the hook for optimizations. So if we take a look at the forward, what they're doing, this might be a bit more clear what's happening. So essentially, if they're using the NOP layer and or the local attention mask is none, then use the global attention mask. Otherwise, we might be using the local attention mask, but this will mean that we are using ROP. This is mainly for optimization purposes and also so we can take a look at the information that's a bit closer to us rather than a bit further from us. So if we use this global attention mask, you're looking at information further from us. Local attention mask, you're looking at information closer to us. And then we pretty much use the attention. We pass through X through the attention norm, then through the attention, and then we add X plus whatever came from the attention. So this is residual connection. And then we do the same for the feed forward. So we pass a age that we got here from through the FFN norm, and then we pass it through the feed forward layer, which can be either MOE or fully dense layer, and then again residual connection, and we return the result out. So now is the time to go to the last big module that's used with this model, and that will be the attention module. The attention module defines a lot of the variables in its constructor, although the most important ones would be the WQ, WK, and WV. Those are the weights or linear layers used for query key and value. Then they also define the cache for the optimization purposes for both key and value that lives on CUDA. But I think a bit more interesting would be to take a look at the forward method here. So the forward method does receive the X tensor, starting position, and also the sinus, cosinus, and sinus frequencies, and optionally a mask. But now if you take a look at the X will pass through the query key and value. So you get the XQ, XK, and XV. Then when you get that, you are reshaping how those tensors look like. And the reason for that is so it can be later passed into the scale.product attention method, which is used to calculate the attention. So this method does expect a certain signature, so you cannot just pass whatever. Once we make sure that we reshape it in the right shape, we check whether we're using the ROPI. If we use it, we apply the rotary embedding. We check whether we use it the QK norm. If we use it, we apply the RMSN norm. Then the next check will be for attention temperature tuning. This is something that's used mainly by Llama models to make a better distinction between the short versus long context, or like as we talked before, local mask versus global mask. Then we fetch the cache, we update the cache with the XK and XV, and then we make XK and XV be equal to the part of the cache that we need for this set of tokens. Once we do that, we make sure that key, query, and value matrices used later match in its shape and size, and then we call the scale.product attention with it. We apply the mask, and we also apply dropout to be 0, which means we don't drop any weights. Once we have the attention output, we transpose some of its dimensions, so we get it back into the original shape, and we pass it through the output projection, so we can get a final output. So this is a standard attention mechanism. So as you can see, pretty simple. And with the exception of few different helper methods, mainly used for optimization purposes, that we import at the top of this script, as well as feed forward and MOE layer. This is pretty much all of the Llama 4 code, and it lives in less than, what's that, 450 lines of code. So it's a pretty simple model. Yeah, that would be it for me today. I hope you enjoyed this video, and see you the next time.